Started.
Hi, my name is Teja-Smart. I will be explaining question D question in the D problem, not question in the uh, Codeforces Round 795. I'll be using board. Okay. You are given an array of n integers. You are asked to find out if the inequality. The inequality is for a pair of indices I comma j, maximum of ai plus 1 epsilon aj. I mean maximum among all the elements from I to j greater than or equals to the sum of all the elements. So maximum should be greater than or sum of all the elements. Holds for all the pairs of indices I comma j where I less 1 less than or equal to I less than or equal to j. So the question is direct, but we cannot solve it. It's not good force. It's not direct good force because n square steps. We have to check for n square pairs. We have to check for every pair if this inequality is satisfied or not. Uh, okay. Each test contains multiple test cases. First line T test case for 10 power 5. First line contains each test case is a single integer n. First line of each is a single integer and then an array of n integers. It is guaranteed that sum of n, the values in the array can be negative or positive, both negative and positive. The values, sum of n over all test cases does not exceed 2 power n. Even though the test cases are 10 power 5, their sum, overall sum will not exceed 2 into 10 power 5. So if we can do it in O of n or O of n log n, the overall complexity would be this 2 into 10 power 5 into log n, which will be 50 or 60, or some it will be O of n log n, or yeah, O of n. If we are able to do it in that complexity, we can do it in O of n squared because if the sum is being 2 into 10 power 5, n squared will become 10 power 5, 10 power 10 like that. That will increase. That will be more than 1.5 seconds. For each test case, on a new line, output S. If the condition is satisfied, means for all the pairs of I comma j, if this inequality that they given here is satisfied, then we should output S. Even if it fails for a single pair, then we should output no. That's it. The question is direct, but we have to think of a way to solve it faster. Like because we can't use O of n square steps, we have to think of a way, or we have to try to do it in a bit fast than O of n square. If you see where I equals to j, will it cause any problem? If I equals to j, maximum of this will be ai, which is greater than or equals to ai. AI greater than or equals to ai is true. So we need not worry about the cases where I equals to j. So to conclude something, we can first see, let's see if this inequality that looks like this would simplify. Like I mean, this inequality which is given for a range of indices from I to j, it would be, it would, we need not, it will happen that we need not worry from for I to j if it is satisfied for I comma I plus 1. It may happen like that. So we will just try to work on this inequality a little bit. If it helps, we can use it, or else we have to think something else. So for I equals to j, it's very clear that it satisfies whatever the array is. If we take two indices I comma I, it's satisfied. So if you try to take indices which are adjacent, I comma I plus 1, suppose I comma j, where both of these are adjacent. The first thing we can say is if this is greater than 0 and this is greater than 0, if both of them are greater than 0, then the sum will be surely greater than both of them because something which is positive got added to it. So it will increase in magnitude. Uh, the sum will be greater than both of them. So sum will be greater than maximum. Then this inequality is failing. So there cannot be two positive elements which are neighboring to each other. Like there cannot be two positives side by side because that surely fails this inequality for I comma I plus 1. Here I equals to I, j equals to I plus 1. For this it's failing. So we can say this in another way, like if there is a greater than positive element, if there is a positive element, okay, we'll also conclude one more small thing. What if all the elements in this array are negative? then the maximum will be negative, and this sum will be the maximum which is negative and plus some sum of negative numbers. It will, the inequality is surely working because it's something greater than or equals to something minus something. So something it's like a greater than or equals to a minus b, where b is positive. So it must work because we are just adding some negative numbers. So if all of these are negative, then it's working. So if an element is positive, the neighboring elements cannot be positive. So they must be less than or equals to 0. Oh, okay, now we have this thing. We are trying to see for I and j, where I and j are a little bit near, like maybe this. Yeah, okay. Okay, let's just try to use this fact and see if we can solve the entire question. Because if we are able to solve using this, just this fact, we'll use it and we'll solve the question. If you are not able to solve this, we'll just try for some other approaches. Because yeah, we are just starting like this. We can try some, if it is wrong, if it's not seeming like it's working, we'll try another thing. Okay, if we take a positive thing, and what else we can conclude? We can conclude some small points, right, which may be helpful later, which using which you can think more. So let's say this is maximum, and we are considering some other interval, some segment. Let's say all of these are less than this. So if we have such segment, if we start from here and take like this, it shows that the sum of all the elements in this plus this thing should be less than or equals to this thing, which means that the sum of all of these side things must be negative, less than or equals to 0. We can conclude that fact also. If this is greater than, not only with this and with this, so this thing is like a smaller part. This thing is like a smaller part of this. So I think because of this, I don't think this has a lot value in solving the question. So okay, if you see this thing, uh, any segment that starts from where I equals to the sum of all these segments must be less than or equals to 0. All means it doesn't go till the end. It goes till whenever all of these are less than this. All of these are less than this. At that moment, if that condition is satisfied, then the sum of all this. We must start from here because we are concluding this using the fact that considering this, we are getting the sum of this as less than or equals to 0. So starting from, if let's call this I, so from I plus 1 to some j, where all of I from I plus 1 to j, where everything is less than the value that we're considering, then the sum of all of this segment should be less than 0. So sum of this, sum of this, sum of this, everything must be less than or equal to 0, and the same goes for this side. Okay, now let's think if it's satisfied for this thing and for this thing, will it satisfy for a segment like this? Because yeah, we can also see now also sum of all of this is negative, less than or equal to 0, and this is less than or equal to 0. Some negative number got added to this, so it will be definitely less than or equal to this. So we can say that if there is something, immediately segments that are attaching to our element. So if there is a greater than thing, immediately a segment which is immediately next to it, and all of the elements in it are less than this, then we can apply this small result that we got, that the sum of that segment must be less than or equal to 0. We just, let's think that we got this result. I will draw this as squares. Okay, we got this results. I think this is not very much useful. So maybe now we'll just try to do the question. Till now, I was just trying to simplify this inequality or get any kind of results that we can get from this inequality. Now the question is, we have to check for every pair if this inequality is satisfied or not. So if you want to check for every pair if this inequality is satisfied or not, it will be like of n square, like which should go for all instances of y and all instances of j, and you have to check the inequality is satisfied or not. It seems like of n square. So but let's try to do, but we have to think of some way to do it in less than of n square steps. For that, we must use some information that we already calculated for some other pairs. to find the newer pairs. If you are using the previous information to find the newer pairs, then we might have we might solve that in a fewer steps than of n squared. So if you are wanting to do that, a normal dynamic programming approach is very common to do such things. Like we have to check for all the pairs. So let's say if you are able to check for pairs that starts from 0 to I minus 1. Okay, let's call this j. We are able to check all, we check it for, suppose we have checked it for all these pairs where I and j both lies in this interval. And now we want to check for a newer element that we added, it's just like extending, like injection. Now we want to check after adding this for all the pairs, now if the inequality is working or not. We want to do in this way. If you are able to do this, then inductively we can solve it for the whole array. And we got if it is satisfied, if every pair is being satisfied in our whole array or not. So after adding this, what are the new pairs that are forming? If you see the new pairs that are forming, j must be equals to this, because if j is not equals to this, if j is not equals to this, I less than j, because I not equals to j, we can assume it from here. I equals to j is not a problem, so I less than j, so I will be before this, j also will be before this, and that goes to, and the pair will be in this segment. That's already done. So j must be this. For a new pair, j must be this, and I will be somewhere in this previous thing that we have. The already computed thing. Now we want to add this and check for all the pairs that involve in this. So the newer pairs are j. I'm taking I this, taking I this, taking I this, all these pairs. So we have a number of pairs as I pairs. It's like O of n. I is like O of n. So we can directly go and check for every pair. We want this O of n. If we do that, it will be n into O of n, because j varies from 0 to n. It will be like n into O of n, which will be O of n squared. So we want this to be reduced to O of log n or O of 1. O of log n and O of 1 means we must be able to conclude the answer for this j. And for all of these i's, I can be from here to here. For all of these pairs, we must be able to complete the answer in less than O of n steps, maybe in O of log n or O of 1. So we must be able to do that. So let's try to do that. So we have to think of a way in which we can solve it faster. What we can solve it faster? For all the pairs where j equals to this and I. Normally, if we don't have any information, we can solve it faster. The information that we will be using here is the pre-computed information that we have. What information we have now is from 0 to j minus 1. We already know that every pair in this satisfies the inequality. We are assuming that because inductively we are going. So we already know this. So using this, we want to reduce this O of n to O of log n using this information. That will be possible because we are using some information. As we are using some information, the complexity would reduce. So we will just try to solve this in less than O of n steps. So it's like checking for j and all the pairs. So we can just, we have to check for all the values of I and j. Let's say this is our new element j, and we have a segment starting from 0, and this is j minus 1. Okay, we have to check for this and for all the values of I. Let's come from backward, because the backward thing will be included in the later things. So coming from that side is better because it's already included. We may also use some information that we got here to the next I. So that's why we will come from back. We will go from I from here like this. So let's say we will see all the values of I comma j pairs for which, something happened. Okay, all the pairs of I comma j for which this thing would be maximum, because then it's a little bit simpler. We know that this is the maximum. So we'll just try to think of them initially, because they're also a set of values of I. And if we can treat all those set of values of I at once or in some fewer steps, our complexity is reduced now. So we got some type of i's for which the last element is the maximum. We can call them okay. So if this is something which is greater than this for the first time, so there is from here to here everything is less than this, and this is the first thing which is greater than this and which is before this, just before this. So let's say all of these are less than this. So if I is in this range from, okay, let's call this as k maybe. If I is greater than k and less than j, then we have this as maximum. So we have now this as maximum, and we want this pair to satisfy the inequality. That's what we are trying to do. For all the values of I from 0 to j minus 1, we are trying to check the inequality using fewer steps. So suppose if the I is over here, somewhere in between, what now we are trying to check it for this to this, for this pair. So as everything is less than this, it's just checking the sum from here to here is less than this value or not. It's nothing but checking the sum from here to here is less than or equals to 0 or not. We have seen this previously over here. When something is maximum and we know that it's the maximum, and when we know that it's the maximum and we have some things which are less than this, if we have a segment, we can easily say, I mean, we have proved or we have concluded that this segment sum must be less than or equals to 0. We have concluded that. So here is the same. So the segment sum for this I, so the segment sum from I to j minus 1. Here we have a condition that I must be in this interval. I must be greater than k and less than j. The interval here k is also well defined, which is k well defined means k is something k has an element which is greater than j, and it is the first thing to have that property. Everything else is less than this. We are assuming that property for k, and we are trying to do this because then that's the maximum value of I where we can use this property for which j will be the maximum, because after this the property is lost for j because this will become the maximum. So till there this will work. So till there it's just verifying if this sum is less than or equals to 0 or not. So now I can go through every I that's in between here and check if this is less than or equals to 0. But rather than that, we can also do something like if all these segments where I goes from k to j, greater than k and less than j, is less than or equals to 0, is nothing but checking the maximum among these segments to be less than or equals to 0. Because if everything is less than or equals to 0, we can conclude that maximum is less than or equals to 0. And if the maximum is less than or equals to 0, everything is less than or equals to 0. So it's nothing but maximum of such things, maximum by varying I, finding the maximum sum of the segment from I to j minus 1. This maximum, if this is less than or equals to 0, then we have done. So we need not go through all the values of I in this interval. We are left with finding verifying the values for I that falls here. We are first seeing these values. I mean, we have to verify for all the values of I because we have to find we have to verify for all the new pairs that form after adding j. So this maximum for this maximum for this sum, we can write that sum as, suppose we have calculated the fixed sums, then we can write this sum as, let's say, p of, this is easier, j minus 1 minus p of I minus 1. That is sum from I to j minus 1. Yeah, this is simple, right? Because we are removing everything that's before I, which is still I minus 1, from j minus 1. Then we'll get sum from I to j minus 1. I to j minus 1. Yeah, so let's say this maximum. Okay, this. So now we want the maximum value of this, which is nothing but the maximum value of this. Here j is constant. J is equal to the index of the new element that we are adding. So j is constant. So it's all dependent on this p of I minus 1. If we want the maximum of this, we want to find the minimum of p of I minus 1. So for k less than I less than j, we want to find minimum of p of I minus 1. So it is nothing but from k minus, from here it is less than, so I minus 1 will be less than or equals to k less than or equals to j minus 2. But okay, let's take j minus 1. I think taking j minus 1 is not a problem because j minus 1 minus j minus 1 will get cancelled and it will be anyway 0, which is less than or equal to 0. I don't think that will cause a problem. So we can just take the minimum from k to j minus 1 among all these pairs. We'll try to find the minimum value and then we will just subtract this from p of j minus 1. And if the value, so the main thing that we are doing is finding the minimum from this k to j minus 1, and then we will subtract that from p of j minus 1 to check for all the values of I that lies between k and j. Okay, now let's come to k. When I equals to k, what must be the condition for this pair to satisfy? Here the maximum is this, and we have already seen if this sum is less than or equals to 0, that's enough for this to become the maximum and the equality to hold. So we will also write that as a condition. So this is very simple condition. This sum to be like this sum to be less than or equals to 0. It's nothing but p of j minus p of k less than or equals to 0. That's it, right? P of j minus p of k less than or equals to 0. That's a simple one-line condition. We can just add it. So for this also it's done. Now we have to see for I less than k. If this thing we can calculate in O of 1 or O of log n steps using some data structures called segmentary or sparse table. So here we have no problem in reducing our complexity from O of n to O of log n or O of 1. We have to worry about this I greater than k, I less than k. The same thing that we have done for this, we will try to extend it for I less than k. So if you're trying to extend this, we will see something where this will be greater than this. So till here everything is less than this. If you try to see for such pairs, I mean this is the first thing which is greater than this. I'm just trying to extend this for this thing now. But I don't think it will be complicated because these things are pre-calculated. So okay, if this is I and this is the max, we have already seen it's enough to check that this sum is like less than or equals to 0 and this sum is less than or equals to 0. It's enough to check that because we have just seen here in the beginning, we have concluded some things about our inequality. That if this is less than or equals to 0 and if this is less than or equals to 0, the sum will be something, some maximum plus something negative, which will be less than or equals to the maximum. So it won't be a problem. Now we are here. Okay, now we are here and this is already less than or equals to 0 because this I comma k pair is already done in our previous computation and it must be a yes because even if one pair is no, we will end our program and conclude the answer is no. It must be an yes in the previous computation that I mean in the previous I, because we are injectively coming step of I increasing I by 1. So this must be negative. And we also know that this is negative because we just now concluded that from k to j pair must satisfy, which means this should be negative. We have also known this. If this is negative and this is negative, it's clear that I comma j is satisfying the inequality. So all the I comma j that are lying in this region also will satisfy the inequality. We need not even check them because they are already satisfying. Because it's so simple now because we need not even check them. We can just leave them because if it is an yeah. But we have to check this thing, if this sum is negative or not. Yeah, if this whole sum is negative or not, we have to check. And we need not worry about this kind of sums because they are all already working. I mean, they are all already computed. We have to only worry about the place where j equals to this new element and I mean, we are coming step by step, like because we fixed the j here. We are only worrying about the new pairs that form. 1 minute. Hello. 1 minute. It's there. Oh, 1 minute. It's not go like this, I guess. Yeah. So now we have to worry about the previous things that are lying here. The I that is before this, and there will be something greater. I mean, we will try to see the same logic. This simplified without doing any other way, without doing any extra work. So if you're trying to see for something over here, then again we have this thing to be less than 0, and we must have this whole sum less than 0 because uh, because this whole sum is less than 0 and this sum is less than 0. So this whole sum is less than 0. Yeah, we can see it clearly. This sum should be less than or equals to 0 because of this pair, k comma this previous. You can call it p comma k. So this sum must be less than or equals to 0, and this sum will be less than or equals to 0. So less than or equals to plus than or equals to will be less than or equals to 0. So for everything, it seems like it's working. Less than or equals, the left sum is being less than or equals to 0. So we won't worry about them. I think it's working. I'll come in a minute. I think it's almost done here. So we have to just verify if this is satisfied for k less than or equals to m minus 1 less than or equals to j minus 1. And we also have to get the previous thing which is greater than this. I have used it without mentioning it very much. We are finding the previous thing which is less than this. The k. The finding of k is difficult here. Difficult means we haven't done yet. So we have to find k. After finding k, it's done. For finding k, I think we can think of it as a prerequisite for the quotient. Like there are like two prerequisites for the quotient. Like we should be able to find the k for all j. Like the first element which is greater than this. For this, there is a procedure using stack. We will find this by maintaining chains like backward and that. I'm not explaining it here. But you can see my code and try to understand it, or you can just try to think of it as your own. I will specify the question very clearly. For each, if there is an array A, for each index J, I'll come in a minute. I'm maybe sorry for that. But given an array A, we have to find an array B. For each index J in array A, we have to find the index K, where A of K is the first thing, which is less than J. A of K is the greatest index, which is less than J, and A of K greater than A of J. Such an element, you understand what is the property of K related to J, right? All of this should be less than J, and K should be greater than J. Such a K we have to find for each J. This can be done using some stack. That's also a GP procedure, like finding for 0 to I and then trying to find for I plus 1. That I'm not explaining it here. that can be done using some stack, something like that. You can Google it, like finding the, I don't know its name, but you can see my code and try to understand it maybe. And the second one is given an array and given two indices L comma R. Trying to finding the local minimum in this in log n or O of 1. This can be done using pre-computation by sparse table or segment tree. Or we can use any of that and we can find this in O of 1 or O of log n. So now, yeah, I'm not explaining these two things. They are like prerequisites. And if we know this thing already, that we can do this, then we can also get the ideas to start dynamic programming or to start to think in this way. I mean, we came directly to that by some other approach, but if you know that we can do these things, then we can also directly, we can more easily do this procedure. Then we can more easily do this procedure. So the code will be now, the code is mostly based on these things. Okay, I will show my code and I will try to explain it. See, I'm making, we need prefix array because we are using it in finding the minimum. So this is taking array input. I will max increase the size. This is array taking input. This is making of prefix array. After that, you can ignore this part. This is for sparse table. After that, you can also ignore this part. This is for question 1 that I mentioned. This is for question 2 that I have mentioned. You can just see these codes clearly and try to understand them, or try to think on your own to find that array B. For an array A, I'm trying to find an array B which will have indices. So okay, this is an array B. So for each j it will give the k. Here B of j will be the k. Okay, here B of j will be the k. So that's simple. Yeah. Now if as we we have to see one thing. Here if j is less than or equals to 0, then we can directly ignore it. If j is less than or equals to 0, take any pair. It will surely work because take any pair, take a maximum in it. If j is less than or equals to 0, I will show it. If j is less than or equals to 0, I mean j means a of j, then take any segment that involves j. Till here, it's already working. So this is just a negative number that got added. It will not affect our inequality. So it will work. If j less than or equals to 0, I'm just skipping it because all the pairs will work. All the for everything for every I, it will work if j is less than or equals to 0. Here j is written as I. It's a little bit confusing maybe. Okay. And now this L equals to B of I plus 1. B of I is nothing but k that I have mentioned here. I wrote it as B of I, and I don't know why I wrote plus 1, but okay, it's plus 1. And R is I minus 1. What we have written here finally is, where is it? Yeah, it's loading. Yeah, j minus 1 comma k. Here k is B of I, j minus 1 is I minus 1. So I'm finding minimum from, I took B of I plus 1 because sometimes this B of I will be minus 1. Just for that case, just for that case, I took minimum from k plus 1 to j minus 1. So it is nothing but k plus 1, j minus 1. By using this, I can get minimum in O of 1 or O of 1 step. That's called using sparse table. Here I am using sparse table. In finding the k, I am using the procedure, stack procedure that I mentioned, the question 1 and question 2. Other than that, it's all this procedure. Finding that this k and it's finding that it's just sufficient to check the minimum. Find the minimum and do this subtraction and see if it is less than or equal to 0. That's what we are using here. So after finding the minimum, and now I am adding k. Because as I took here k plus 1, here I am adding k. Here I am adding k. And I'm taking care of the case where b of I equals to minus 1, because in that case I should be a little bit more careful. After that, I'm just checking if prefix of f of I minus 1 minus I minus 1 is j minus 1 here, same, minus the minimum. Minimum is f, I'm showing it in the f, greater than 0. Then it failed, CO no, return, because if it fails, we are returning. And then this is the condition for, I have clearly told here, for this condition we can verify it separately where I equals to k. this is for I greater than k. This is for I greater than k, and this is for I equals to k. For I equals to k, if you remember, it's just to check if it is greater than 0 or less than or equals to 0. For I equals to k, this is the maximum, and this whole thing should be less than or equals to 0. So it is, if this happens, no, or else yes. And for I less than k, we need not verify at all, because we found that it's already working well. So it's already being correct. So in these two cases, it's no. So if these two cases, if it doesn't happen, if it does, if a no doesn't occur here, then it's satisfying. Then for all the pairs of I comma j is respecting or is satisfying that inequality. So we can go for the next I, and inductively it will work for all the i's. Hence the answer will be yes. I think this is what I'm saying. You can try to re-listen the part that I have told here, because I made steps, I made some things, and then I have used it at a later stage. So it would be like we don't remember the things that we have used it here, because I've told that for j and k we are separately verifying it. For I k greater than I, k less than I, we are using this. So for k less than I have used this, and for k equals to I just verify it. I just wrote a code and I'm verifying it. The main thing, the overall logic, the main logic part that we have used is nothing but the main thing that we have used here is this thing. I mean, we didn't used it directly after concluding that. We have used it slowly. The main thing that we have used is uh, if all of these are less than this, they can be like anything like this in between. Then this sum should be less than or equal to 0. That's the fact that we kept using to prove that for I less than k, the answer is yes. To prove that for k less than I, the answer is just about seeing this maximum less than or equal to 0. So we are using only this logic to find those facts. And I mean, yeah, that's it, I guess. The 1 and 2, it's about sparse table and this code to find the array B for array A. After that, I think I have proved perfect. I have proved entirely about the question. If there are any doubts, maybe mention in the comments. I'll try to answer them. Okay, thank you. That's it, I guess. Yes, Ram.